The problem started with a routine safety check. On November 5, 2025, just hours before the Shenzhou 20 crew were set to undock from the Tiangong space station, mission controllers hit the brakes. The reason? A suspected impact from microdebris on the return capsule's window. In the increasingly junky environment of low Earth orbit, these kinds of hits are a constant threat. What seemed minor was actually a catastrophe waiting to happen. The scorching heat of re-entry could cause a cracked window to fail, leading to the instant loss of the vehicle and its crew. The Shenzhou 20, their ticket home after a record-breaking 204-day mission, was suddenly a death trap. This left the China Manned Space Agency, CMSA, with a pile of problems. The 3 Shenzhou 20 taikonauts were stuck. Their replacements, the Shenzhou 21 crew, had just arrived, meaning the Tiangong station was now supporting 6 people and straining its life support. But the most critical issue was the lack of a reliable escape pod. In case of a fire, a depressurization, or a medical emergency, there was no way out. For most of spaceflight history, this would have kicked off a desperate, months-long scramble to prep a new rocket. But China didn't need months. They had a plan. The question in control centers around the globe was, what now? The answer came with shocking speed. China immediately activated a contingency plan. While the public saw a launch 16 days later, the real work had started years before, with a system designed for this exact moment. The launch of the uncrewed Shenzhou 22 spacecraft on November 25th was the visible solution. It soared into the sky from the Gobi Desert, a robotic lifeboat sent to give the stranded crew a safe ride home. It docked with the station just about 4.5 hours later, a clean, efficient end to a tense 20-day saga. This rapid launch was hailed as a masterclass in handling an in-orbit emergency, a testament to China's skill. And it was. A 16-day turnaround from spotting a critical failure to launching a replacement is unprecedented. But that number, 16, is also misleading. It's the time it took for this specific real-world event, which involved a complex chess game of risk assessments and the clever, unplanned maneuver of using the newly arrived Shenzhou 21 to bring the Shenzhou 20 crew home first. The real story, the one that should have every other spacefaring nation paying attention, isn't the 16 days it did take, but the 8.5 days it could have taken. This capability is called the rolling standby protocol, or sometimes launch on demand. It's a strategy China has been building into its space program since the Shenzhou 12 mission. The idea is simple, but pulling it off is mind-bogglingly complex. For every crew sent to the Tiangong space station, a complete backup rocket and spacecraft are kept nearly ready to go on the ground. This isn't just about having spare parts in a warehouse. We're talking about a fully integrated, vertically assembled Long March 2F rocket with a Shenzhou spacecraft already on top, sitting in a dedicated building just a mile from the launch pad, waiting to be rolled out and fueled. It's a dedicated team, on call 24/7, ready to compress a standard 45-day launch campaign into just over a week. This changes the entire game of space station operations. It treats low Earth orbit not as a distant frontier, but as an extension of sovereign territory, one that can be reached and supported with unbelievable speed. So how did China build this system? What are the specific engineering tricks, the unique hardware, and the tough procedures that make the world's first rapid space response a reality? To get the rolling standby protocol, you have to understand how it breaks from the pack in human spaceflight philosophy. For decades, space rescue was more theory than practice. The dominant idea, shaped largely by NASA, was all about self-rescue and having redundant systems on the spacecraft itself. Apollo 13 wrote the book on this. When the command module failed on the way to the moon, there was no help coming from Earth. The lunar module, Aquarius, had to become a lifeboat in a brilliant act of desperation that proved there was no other option. Even with Skylab in the 70s, the rescue plan was a just-in-case idea, not a permanent policy. A rescue vehicle was prepped when one crew's Apollo capsule had thruster problems, but it was a massive, one-time effort. In the end, the rescue wasn't needed, and the hardware was stood down. The space shuttle era had its own rescue plan, born from the Columbia tragedy. The Launch on Need mission meant that if a shuttle was too damaged to return, the crew would shelter on the International Space Station, while a second shuttle was rushed to launch and pick them up. This was a lifeline, but a shaky one. It only worked because the ISS was there as a safe haven, and it completely depended on another multi-billion-dollar orbiter being far enough along in its complex and lengthy prep schedule. Today, NASA's Commercial Crew Program relies on dissimilar redundancy, with both SpaceX's Crew Dragon and Boeing's Starliner. The idea is that there are usually two different, fully functional lifeboats docked at the ISS. If one breaks, the crew can just use the other. This removes the need for a frantic rescue launch from the ground, because the rescue vehicle is already there. But this strategy has its own weak spots. It depends on having multiple, healthy commercial partners. The long delays and technical headaches that plagued Boeing's Starliner program show you can't always count on that. China has chosen a totally different path. Their approach isn't redundancy in orbit. It's guaranteed rapid access to orbit. As the sole operator of its own station, Tiangong, the CMSA decided that the only acceptable safety net was a dedicated rescue system under its direct control at all times. It's a much more expensive and demanding approach, requiring almost a parallel universe of manufacturing and launch infrastructure. But it delivers one thing no other system can: a sovereign, on-demand capability to reach their astronauts in days. This isn't just about safety, it's about control. The power to launch in 8.5 days isn't magic. It's the result of smart engineering centered on one place: the Jiuquan Satellite Launch Center in the Gobi Desert. And at the heart of it all are two key pieces of hardware: the Long March 2F rocket and the Shenzhou spacecraft. Let's start with the rocket. The Long March 2F is a bit of a legend. While the rest of the world moved on to new fuels and designs, The 2F perfected older technology. And funnily enough, its old tech is exactly what makes it perfect for this job. It's a two-stage rocket that uses hypergolic propellants. These fuels aren't as powerful as the super-chilled liquid hydrogen and oxygen in many modern rockets. But they have one massive advantage. They're storable at room temperature. Cryogenic fuels have to be loaded just hours before launch because they boil away. That's a complex, dangerous, and time-consuming process. Hypergolic fuels, on the other hand, can sit in their tanks for long periods. This means a Long March 2F can be fully assembled and kept on standby for months, dramatically shortening the pre-launch timeline. What's more, the Long March 2F is one of the most reliable rockets ever built, nicknamed Shenzhou, or Divine Arrow, for its perfect record on crewed launches. It's human-rated from the ground up, with a launch escape system to pull the capsule to safety if things go wrong on the pad. This combination of reliability and storable fuels makes it the ideal vehicle to have waiting in the wings. The second piece of the puzzle is the Shenzhou spacecraft. It's heavily based on the Russian Soyuz, but with some key Chinese upgrades. Its orbital module has its own solar panels, allowing it to function as a separate satellite for months after the crew returns. A clever bit of multitasking. For the rolling standby protocol, a complete shenzhou is attached to its Long March 2F rocket. It's kept in a manned-ready state, even if its first job is an uncrewed rescue. For the Shenzhou 22 rescue, the spacecraft was even preloaded with supplies, including fresh food and repair equipment for the damaged window on Shenzhou 20. This pre-integrated stack is kept in what might be the most important building at Jiuquan, the Vertical Assembly Building, VAB. Inside this massive, climate-controlled facility, the rocket is assembled vertically on a mobile launch platform. This is a huge time saver. Instead of building the rocket horizontally and then lifting it upright at the pad, the whole 62-meter-tall assembly is prepped indoors, protected from the harsh desert elements. When it's go time, the entire platform just rolls out of the VAB and makes the 1-hour, 1.5-kilometer journey to the launch pad. China has weaponized the efficiency of this process. These are the physical parts, but how do you get them into orbit in just 8.5 days? That's all about procedure. So, what would that ideal 8.5-day sprint to orbit actually look like? While the exact internal checklist is a state secret, we can piece together a very clear picture based on the engineering. It would be a masterclass in choreographed chaos. Day 1. Activation and rollout. The moment an emergency is declared on Tiangong, the plan kicks into high gear. The standby Long March 2F and Shenzhou, waiting patiently in the VAB, undergo final health checks. Standby teams at Jiuquan are mobilized. The main event of the first 24 hours is the rollout. By the end of day 1, the massive VAB doors would open, and the entire stack would begin its slow, steady journey to Launch Pad 921. Day 2 to 3. Pad connections and initial checks. Once at the pad, a swarm of activity begins. Teams work around the clock, connecting the hundreds of electrical, data, and fluid lines between the launch tower and the rocket. These are the vehicle's lifelines on the ground. Technicians would then power up different systems on the rocket and spacecraft, making sure everything is perfect after the move. It's meticulous, checklist-driven work, where every connection is triple-checked. Day 4-5, system-wide integrated testing. This is where they test the rocket and spacecraft as one brain. Controllers in Jiuquan and Beijing would run full dress rehearsals, simulating the entire mission from liftoff to orbit. They'd send commands and verify that every system responds exactly as it should. The guidance computers would be loaded with the final flight path, calculated to intercept Tiangong at the perfect moment. Day 6, fuel loading preparations. With all checks passed, the pad is cleared for the most hazardous part of ground ops, loading the hypergolic propellants. Safety zones are established, and the automated fueling systems are prepped. This is a critical step, as the fuels are extremely toxic and corrosive. The teams responsible are specialists in protective gear, following incredibly strict protocols. Day 7, propellant loading. An entire day is dedicated to carefully pumping the dinitrogen tetroxide and unsymmetrical dimethylhydrazine into the rocket's tanks. Because the fuels are storable, there's less time pressure than with cryogenics, but their toxicity means the process is slow and methodical. Once loaded, the rocket is considered wet, and access to the pad becomes heavily restricted. Day 8, 8.5, final countdown and launch. The final day is a whirlwind. One last system-wide health check is run. Weather is monitored constantly. Though Jiuquan's desert location usually provides clear skies, a key reason the site was chosen in the first place. The mission controllers run through their final checklists. In the final minutes, the umbilicals retract, the rocket switches to internal power, and at T0, the engines ignite, lifting the divine arrow off the pad. About 10 minutes later, the spacecraft is in orbit. A few hours after that, using a fast docking profile, it would arrive at the Tiangong space station. From crisis to lifeboat docked, 8.5 days. It's a timeline that feels almost impossibly fast, and the 16-day response for Shenzhou 22 proved that even with real-world curveballs, the core system works. This procedural speed, built on smart hardware and dedicated infrastructure, is what truly sets China's capability apart. The ability to launch a human-rated rocket in 8.5 days is more than just a cool engineering feat. It's a strategic game-changer. First, it totally redefines astronaut safety. The rolling standby protocol gives the Tiangong space station an external, ground-based lifeboat system, while other stations rely on the capsules already docked. Tiangong has a guaranteed replacement ready to go. This drastically reduces the risk of a stranded crew scenario, turning a potential catastrophe into a solvable, though still serious, problem. As one Chinese official put it, it reflects a supreme respect for life. Second, it changes how you run a space station. A station that can be resupplied or evacuated on a week's notice is a much more robust and flexible platform. It allows for bolder science and more complex work. Knowing a backup plan is always within reach. It makes Tiangong less of a remote outpost and more like a permanently supported piece of territory in orbit. This leads to the third, and maybe most important implication: the geopolitical angle. A rapid launch capability is inherently dual use. A system that can launch a rescue ship in 8.5 days can launch other things just as quickly. This could mean replacing a critical spy or communications satellite in a crisis, or deploying a new military asset with blinding speed. In a conflict, being able to quickly replace your eyes and ears in space is a massive strategic advantage. This capability puts China in a unique position of leadership. They are now the only nation with a proven, rapid space rescue system. Imagine a crisis on the ISS where the American and Russian vehicles are unavailable. A Chinese offer to launch a shenzhou rescue would be hard to refuse and would carry huge geopolitical weight. It challenges the historical leadership of the US in space and forces a tough question. Is the current model of relying on commercial partners enough? Or is a dedicated rapid launch rescue capability now required to maintain strategic parity? Breaking down this level of engineering and strategy is what we're all about. If you're finding this look behind the curtain valuable, do us a favor and subscribe and hit that notification bell. It lets us know we're on the right track, and we want to hear from you in the comments. Do you think NASA and its partners need to build their own version of a rolling standby system? Or is having multiple capsules at the ISS good enough? Your insights are a huge part of the conversation, and we read them all. The story of the 16-day launch is a perfect example of how the biggest breakthroughs in space are often the invisible systems, not the spectacular events. The world saw an impressive emergency response, but the real innovation was the rolling standby protocol, a system years in the making, built on smart engineering and a massive logistical commitment. China has successfully married the old-school reliability of the Long March 2F rocket and its storable fuels with the modern efficiency of vertical integration and rapid rollout. They've built the infrastructure and trained the teams to turn a months-long launch campaign into an 8.5-day sprint. They've created a philosophy of guaranteed access to orbit that stands in stark contrast to the models used by other space powers. The result is that China has turned space rescue from a theoretical longshot into a repeatable, real-world capability. They have built a safety net for their taikonauts that is second to none, making their space station the most robustly supported human outpost in history. But this is about more than just safety. It's a clear signal of Beijing's long-term ambitions, a dual-use technology that serves as both a peaceful rescue tool and a powerful strategic asset. This isn't just a new benchmark for safety, it's a new benchmark for what it means to be a leading space power. And now, the world has to decide how to respond.